Good afternoon, everyone, and welcome to MOS Live. My name is Katie. My pronouns are she, hers, and I'm going to be helping our presenter out today with our MOS Live presentation of Science in Action, Flying is Complicated. If you're watching on Zoom, please know that you can ask us questions or make predictions by hitting the Q&A button at the bottom of the screen. And we're even going to have some polls for you today in order to chat with us as well. And if you're watching on Facebook or YouTube, we are terribly sorry, but we cannot take any questions from there at this time. Also, if you would like to see closed captioning, you can hit the CC button at the bottom of the screen. At this point, I invite our presenter to turn on their camera and introduce themselves.
Hello, friends. My name is Matt. My pronouns are he and him, and I'm thrilled to be presenting this program from the Museum of Science. We have returned to being open, and it's great to see visitors in the hall and also to get to use some of the cool stuff that we have here. We are still waiting for some fancy cameras to come in, so apologies if sometimes things are a little bit overlit. And they're also doing construction downstairs, so we got that going on too. But who cares? Let's have some fun. And flying is an especially fun topic. It's such a neat area of physics. It can happen in so many different ways. And if you wonder why I call this program Flying is Complicated, it's because one of the things I've really come to appreciate is just how many things go into the kinds of flying vehicles we use. Now, I do want to start with just establishing some basic ideas. So I've got a ping pong ball here. And if I hold this up and then let it go, what do we think is going to happen? Now, Katie, is this one of the polls we have?
It is, so I'm launching it right now. We have what will happen to the ball? Will it fall, fly, or disappear?
All right, everybody, we need your votes. I'm not allowed to vote, apparently, so we're counting on you. We'll give you 5 seconds. 5,
Coming in very quickly.
3, 2, and 1. Polls closed. What do they say, Katie?
Awesome, everyone. All right, we have 94% of you who voted think it will fall, along with a couple who think it might fly or disappear.
Absolutely. The program's about flying. Maybe I'm doing something secret. Let's find out. 1, 2, 3. It falls. It's just an ordinary ping pong ball. I didn't do anything special to it. Now, the reason it fell is because of the same reason everything falls on our planet, because of something that exists between this ball and the planet Earth. Do we have a poll on that as well, Katie?
Yes, we do.
Awesome. I thought you might. So what exactly is it that makes the ball fall?
So what force acted on the ball when it fell? Frictional, magnetic, or gravitational?
All right. Once again, I'm going to give you 5 seconds. 5, 4, 3, 2, and 1. What do we think?
All right. Wow. We had 100% of people who responded say it's gravitational force.
Nice job. Nice job. Those other forces are important as well, but in this case, we even get results. Very cool. But in this case, it was definitely gravity. Now, that word force is something we're going to use a lot, so it makes sense to define it. In science, a force is simply a push or a pull that can change how it moves. And gravity is a force between objects. So there's gravity between this ping pong ball and the planet Earth that pulls them together. And yes, I said that intentionally, pull them together. More on that in a few minutes. So if I let go, it's normally going to fall. Now, I could do something different. Instead of just letting it go, I could apply a force with my muscles straight up. And I think this one's not a polled question. Am I correct, Katie?
Correct.
Okay, so I'll just do this. You can sort of make your internal guesses, but you notice that if I hurl it, we give it a force upward with my hand, the ball goes up, and I managed to dent it again. This is my only ball. All right, let's see if I can fix that while we're doing this. Whew, good. I have a future as a car dent fixer. Because basically those were 2 cases where we had unbalanced forces. In the first case, when I let go of the ball, the force down from gravity was the strongest one, so that's why it moved down. In the second case, the force up from my muscles was stronger than the gravity down, so that was an unbalanced force up, so that's why it went up. And then, of course, there's a middle ground. Is it falling right now, or is it shooting up in the air right now? You can answer in the Q&A.
All right, let's see what we have coming into the Q&A. No, it is not falling. It is not going up. It is staying still.
Except for the tiny motions, due to me being old and having muscles that are a little quaky at times. Plus, I did a really hard workout this morning. So, but yeah, basically right now, the forces are balanced. There's still that downward force from gravity, but there's an upward force, and that upward force is from my hand. And I know that right now it doesn't look like my hand is pushing in the same way we tend to think of a push, but it is. It's pushing up just as strongly as gravity's pulling down, so forces are balanced. So this is at the heart of whether anything moves. Are there balanced forces or unbalanced forces? And in the case of flying, when you have something that has those unbalanced forces, those forces balanced out, meaning the force of gravity down is balanced by some sort of a force up, we have a big fancy word for that, and it's an important one. It's called equilibrium. Now, because it's such an important word, I think Katie has a slide she can show you. I always like to make sure we have at least a few different ways to learn words. So equilibrium just means when forces are balanced, and it's why this ping pong ball isn't falling down. Thank you, Katie, that's perfect. But it's also why some things maybe don't fly, but float. Now, if we take away the slide, Katie, what I'm specifically saying is there are things like balloons that, if they're tethered, they're going to just float there. I don't really think of that as flying if they're just in equilibrium because they don't have any control of where they go. But what we try to do is we try to come up with things that have an equilibrium, that have some force up to keep them from falling down, but also have something called thrust so they can move themselves around. That's where we get into true flying machines, and more or less they fall into two categories. Now, I think Katie has a slide of those two categories. Is that correct, Katie? Awesome. There's basically two categories of flying machines. One are ones that are lighter than air and ones that are heavier than air. Now, lighter than air ones are things like blimps, like that example there, zeppelins, basically anything that's filled with a gas that's lighter than the atmosphere around it. They end up being pushed up by the atmosphere through a property called buoyancy, and that's what gives those things the equilibrium to not fall down unless they control that. And in addition, those machines also have little engines on the side to push them around. Now, lighter than air vehicles are wonderful and useful, but by and large, most of us travel in heavier than air vehicles, and that's basically a fancy name for things like airplanes. We don't generally want to fill an airplane with helium because then the flight attendants will sound like this when they're asking you if you want coffee, and it would create other issues as well. So heavier than air machines like aircraft have to use a different kind of force to hold them at that equilibrium, and that force is called lift. That's what we're going to explore in this program. But they also typically have engines to drive them, or if there's something like a glider, they're basically using gravity to give them some forward motion to start with. So thank you for that slide, Katie. This is where it gets a little bit complicated, because when you read science books about lift, you come up with all kinds of concepts. And honestly, scientists argue about how much some are important than others. So I'm going to take the longest road possible and show you examples of all of them. And we're going to start with one that's called Bernoulli's principle. Now, Bernoulli was an Italian dude who lived a long time ago, and he noticed through studying sewers, by the way, that whenever a fluid went through something that was narrow, it sped up and it didn't exert as much force on things around it. Now, that word fluid is something we haven't mentioned yet. And a fluid is basically any way of any kind of gas, like our atmosphere, or a liquid, like the water that's in our oceans. Those both can flow, and that's why they're called fluids. Now, I want to give you a little example of Bernoulli's principle. So to do that, I'm going to change the angle of the camera a little bit. I have here a straw with a little funnel on the end. I've got my ping pong ball, which fortunately I was able to fix because this wouldn't have worked otherwise, and I foolishly didn't bring up a spare. Now, if I were to blow through the straw at the ball, most people would have a certain expectation of what would happen. Is this a poll question, Katie, or should I just go for it?
It is not.
Okay, so what I'm going to do is I'm going to put this in. I'm going to start blowing, and if you want to make a prediction about what's going to happen, you can do that through the Q&A to Katie. But I'm going to stop talking and start blowing. Here we go. 1, 2, 3. Now, while I was blowing, because I did run out of breath, you may have noticed something that probably you found a little curious. Let me do that again. What happened while I was blowing? Did the ball come out or did it stay in the funnel?
The ball is stuck in the funnel.
Stuck. Now, some of you might have thought maybe I did that by gluing it to the funnel or something, but you saw clearly that when I stopped blowing, it fell out. Or maybe some of you thought that instead of blowing, I was slurping, that I was sucking the air through and that was keeping it in there. I'd like to try to prove that isn't the case. So I'm going to do that one more time. Third time's about all I can do before I start to hyperventilate, and that's bad. So what I'm going to do is I'm going to do it next to this little fringe of paper. And with any luck, if I do it at the right angle, you'll see some of the paper move as the air comes out of the funnel, not into it. Okay, one more time. I got this. Did you see the paper move a little bit? One more time. I think I can do this again.
Yeah, especially those little ones on the edge.
Yeah, I was trying to cut them all that skinny, but man, it is a pain to cut a little skinny piece of paper like that because I keep cutting through them. I promise you, there's no trick here. I am blowing out. And the reason that happened is because as the air forced its way through that really narrow gap between the ball and the funnel, it was like the fluid going through narrow sewer pipes for Bernoulli. And what happened is as that air pushed its way through those little gaps, it started moving really fast and it didn't push as hard on the ball. Now, wait a minute. I just realized I forgot to point something out here, which is that gravity is not the only thing that can apply a force. In fact, there's lots of forces. Katie also mentioned magnetism and friction, but air can also apply a force. If you want me to prove that in a fairly simple way, I've got a thing here that a lot of people will probably recognize. This is called a suction cup. I'm sure a lot of you have smaller suction cups in your house that maybe hold things on the window. This is an industrial one that's actually meant to move things around. And all it is a piece of rubber. It's got a little hollow in the middle. That thing in the middle is not a magnet, by the way. People sometimes get confused by that. All it is the steel handle that holds it together. But the point is, since there's that hollow area, that's a place where we can hold some air. Now, if I tilt it down and just put it on the table like so, and then if I grab the handle in a moment and lift, Katie, I think you have a pull for this one, don't you?
Do.
Okay.
So what will happen when Matt pulls up on that handle of the suction cup? Will it stick on the table or will it lift up?
All right, let's see. And once again, I'm going to give you 5 seconds, partly to move the program along and partly because when the poll is up, I can't see my little camera window. 5, 4, 3, 2, and 1. What do we have?
Awesome. This one is a little more split. More people think it will be stuck to the table, though.
Mm-hmm. I love that that there's a difference of opinion, though. That's such an important part of science. And I have a feeling that for anybody who thinks it will lift, you might have noticed I didn't do something important because if I do lift it, it will come up. Because if you've used suction cups, you probably know that one thing you have to do is you have to push them or mush them. Pushing them or mushing them, whatever push word you like, basically squeezes the air out of the middle. So I'm going to do that now. Okay. You didn't see it squirt out because air is usually invisible, but there's less air on the inside now to push it up. There's still air on the outside to push it down. So now if I try to lift it, oh my goodness gracious, I'm going to lift the whole cart if I'm not careful. Since that's a little hard to tell if I'm just faking it or not, I'm going to peel it up to let some air in. And I've got a piece of plastic back here. If I sort of whomp it on, same deal. I squeeze the air out and now the air can't push it off the plastic, but there's air on the outside pushing it onto the plastic and it's on there pretty strongly. I don't want to wreck my nice thing because this is something that I made that I'm hoping someday we'll actually get to use, but I can give you one quick sort of large scale demonstration of just how strong the push of air is. I'm going to pivot the camera to where there's a big white thing in the back and all that is we call it Stanley actually. It's like a giant thing on wheels with a big piece of plastic on the front. So I'm going to do that same thing. I'm going to slap this on the front to squeeze out the air and then show you just how strong that push of air is. Okay. Hang on, popped off. Let's try that again. Strong enough to move Stanley. So air pressure, the push of air, is an extremely strong force, and it's something that can be changed in a number of different ways. So one way is by speeding it up. Now, that's one thing involved in how things fly, but another one that's important is an idea called Colander Force. This I'm not going to demonstrate live because there's such a cool thing to show it that unfortunately I can't do inside this theater. But I went down to our chemistry lab yesterday and recorded it. So what Katie's going to do in a moment is put up a video of some water coming out of a sink faucet, and then I'm going to stick a curved piece of plastic, like a bottle or something, into the stream. So Katie, do you mind playing that video? And it'll run for about 15 seconds. Now you notice that when the bottle goes in, the water curves around it. It doesn't like splatter randomly. The water seems to follow the edge of the bottle because that's what Colander Force is. Colander Force is sort of a stickiness that fluids can have, and it everything that's going on is a bit more complicated. It involves a concept called entraining and how a stream of fluid sort of gathers in fluid around it. And this is a 30-minute program. But basically, the idea is that when you have a moving fluid, it follows around things and sort of add a stickiness to it. So Colander Force is another factor in how things fly, but there's more. There's Newton's third law. Now, do you remember earlier when I was talking about the ball and the earth pulling on each other? I said I'd explain more. You see, Newton was a scientist. You notice all these awesome scientists get to have things named after them. So that's why it's cool to discover things. All I have named after me is a tool in the shop. It's not very exciting. So screwdriver. Anyway, so basically, the reason the earth and the ball pull on each other is because Newton just found out a long time ago that forces act in pairs. Whenever you push something, it pushes back. When you pull something, it pulls back. So if there's a pull between the earth and the ball, there's also a pull between the ball and the earth. Now, fortunately, because the earth is so humongous, we don't have to worry about it moving very far from the pull of this teeny tiny ball, but it is there. It can be measured. And I can show you Newton's third law in a different way using this balloon. Now, I'm going to blow up the balloon. I'm just going to tilt this so that you can see my little bit of paper again. Whew, all that blowing through the straw really wears out your lungs, Katie, I got to tell you. Now, I'm holding the balloon so it's aimed straight up. And if I let go, I want a prediction of what will happen. And I think Katie has one last pull. Yep, there it is. Okay, Katie, we are the team supreme.
So what will the balloon do? Fly, fall, or maybe burst?
I hope it doesn't burst because I don't have my proper PEPB on. My boss would kill me. All right, 5, 4, 3, 2, and 1. Are we ready? 3, 2, 1, and ooh, we seem to like fly up, but let's find out. All right, 3, 2, 1, and liftoff. Now it does fly up. After a few seconds, it starts going anywhere it feels like, because balloons are not exactly guided missiles. But the reason it went up has to do with Newton's third law, because if the balloon goes up, something has to go down. That's the way it is. And probably a lot of you can guess what's going down. It's what was in the balloon. It's the air. Now, if I want some proof that that's the case, I can hopefully demonstrate that to you. Let me get out another balloon. I'll keep it the same color. I'll try to blow it up to the same size.
There's that option.
That one, I heard a little hiss as I was blowing it up, like I would say, please survive, please survive. That's why we always have spares, children. Unfortunately, this one is a green one, so hopefully nobody will think that the green one is significantly different. I don't care as long as it doesn't explode in my face. All right, and apologies, by the way, that must have been terribly loud through the microphone. I swear I didn't do that on purpose.
It was okay, it was okay, don't worry.
Good, okay, here we go. Afraid to make it go any bigger this time. So I'm going to do it the same way. I'm going to aim it up, but this time I'm going to put the end right over my little frill of paper. And you should, with any luck, see some evidence that as the balloon goes up, the air is going down. 1, 2, and 3. Did you see the paper move a little? I'm going to take that as a big yes.
I saw the paper move.
Awesome, cool. All right. So basically, Newton's third law is saying that if anything goes up, something's got to go down. And this impacts an airplane as much as it does a balloon. If the airplane's going up in the sky, somehow some air has got to be going down. And then, because of course, flying is complicated, there's one more thing I want to share with you. And it's one of the trickiest ones to describe. It's called angle of attack. It's not named by some dude or woman named Angle. It literally means a math angle. And it basically has to do with the idea that when air is flowing over things, sometimes the angle at which it hits depends. So to show this in kind of a crude way, I'm going to tilt my camera so it's like right at the edge of the table. I've got a little ring of paper, which we're going to use for something else in a couple minutes as well. I'm going to put my ping pong ball back on it. And I'm going to actually sit on the floor because this is like super low. Oh, and I squished my straw. It's already pretty gross. Okay. Now I've got here a straw. You'll notice it's made out of paper. I did that intentionally because if you want to try this at home, you can actually do this pretty easily. I'll tell you more about that in a moment. But what I'm going to do is I'm going to first blow over the top of the ball, and probably what will happen is it'll scoot out the cup. 1, 2, 3. Yep. You notice, oh, other side of the table. You'll notice that it went away from me because at that angle, basically all the forces acting on the ball were basically pushing it in the opposite direction. But Watch what happens if instead of doing it at that angle, I do it at this angle. This is a little tricky, by the way, so bear with me. Might take 1 or 2 tries. Once more, then I think you'll sort of get the point here. Sometimes I can get it to come down for a landing. Nope, too hard. Hang on. I got to finish better than that.
It is doing something different, so we're getting there.
Yeah, I'm just, I think at this point my lungs are. Well, I didn't get the landing, but you got the point with that last one. That was a pretty good one. Basically, by angling the airflow in the right way, all the forces acting in the ball were pushing up, okay? Even though the straw certainly wasn't below it. And it just means that angles have a big effect on things too. Now, this is where I'm going to sort of circle back to the title of the program, which is called Flying is Complicated. In a lot of science programs, you end up saying, and the reason this happens is because of blank. Well, we have 4 different ideas that all seem involved in flying. And Katie, I think you have a slide of them, right? I always like to put up the terms since we have so many. And to go over them again, we have Bernoulli's principle. We have Colander Force. We have Newton's third law, and we have angle of attack. And I've noticed in my research on this that a lot of physicists and engineers get very high strung about which of these is more important. And I would argue that most, if not all of them, at least contribute in some way to flight. Getting more into it involves studying in detail fluid dynamics, which is something, frankly, I don't know how to do and don't want to describe in such a short program anyway. But it also depends a lot on the type of plane and how it's flying. Now, where all these things do sort of work in are the things that help give an airplane equilibrium, which are its wings. And Katie, if you have a picture of, I think there's a picture of the wing right after the picture of the terms. Maybe we could show that. Wings can come in many different forms depending on the type of airplanes. But if you ever go and look at a commercial jetliner, like the one that is going to pop up any second on the screen. Nope, that's going the other way.
Sorry, y'all.
That's okay. We already learned about Colander Force.
I know, right? It was just so good. I just wanted to learn about it again.
Okay. Awesome. Thank you, Katie. You may notice that that wing has a curve to it, and it has slats and things that come out of the front of it that can give it even more curve under the right circumstances. Not all wings are curved. Some of them are flat, especially with certain kinds of high-speed jets, aerodynamic jets. So basically, what I'm going to say at the end may not be very satisfying. I'm not going to give you one reason that all airplanes fly. It has to do with a combination of circumstances, and that combination depends on the type of airplane and how it's flying. But I do want to end you with something you can do yourself and something big. So Katie, you can turn off the slide now, please. I want to show you a way that you can actually try that thing with the ping pong ball at home. Now, you can try it yourself with a ping pong ball if you have one around. They do work the best because they're nice and stable. It does take a little while to get the hang of the blowing, as you clearly saw, and be really careful about hyperventilating. So if you feel out of breath or see stars, take a break, okay? For a straw, by the way, I didn't use a plastic straw. I just made myself a little paper one. I wrapped some paper around a nail I found, and that worked quite well. So if you don't have a straw around your house, just make your own. And then I just taped it together. And if you don't have a ping pong ball, I tried something that actually worked pretty well. I made a little ring of paper. You know, I made it kind of small, but you notice it's got a nice curve to it. And what I'm going to try to do is put it on there. And once again, if I can blow on the top with the right angle of attack, hang on, this worked really well in practice. Part of the problem is my straw is getting a little moist right now, so. All right. I'm getting out of breath, but the point is, if you practice with this, I was able, especially when I was standing up and not crouched on the floor, I was actually able to get this to go up and sort of stay up like this, as long as I had air flowing over it the right way. So try it yourself. Again, just be mindful of the whole hyperventilation thing, but this is something easy you can try at home if you want to experiment a little bit with a couple of the things that go into airplane flight. But I also want to show you something really big, because I'm really excited to be back in the museum. We've got all sorts of great toys. And what I'm going to do is show you these principles in a very dramatic way. When I was turning the camera before, you may have noticed that there's something very bright and colorful back there. It's a giant ball, a nylon ball that's filled with air. It's only half inflated right now, which is why it's looking kind of sad. What I'm going to do in a moment is I'm going to go back there. I'm going to top off with the air so it's completely round. Then I'm going to use a blower. Might be a little loud, so if you're sensitive to sound, maybe turn down your volume. I'm going to use a blower, and by angling it in just the right way over the surface of the ball, I should get the ball to go up. Then I'm going to try to reach equilibrium. I'm going to try to reach a point where it sort of floats, where it's perfectly balanced out between the forces of air pushing it up and the gravity pulling it down. And then for my final trick, to make it truly fly, I'm going to change the position of the airstream from the blower to try to pull it towards the camera. And if I'm really lucky, I might even be able to bounce it right off my computer. So let's see how we do with this. It should only take about 30, 40 seconds. And after it's done, I think we have time for a couple of questions if anybody has any. So let me see if I can end this program about how complicated flight is by showing you something flying in kind of a cool way. All right, here we go.
All right, thanks, Matt. And while he's doing that, just a reminder, if you're on Zoom, you can head to the Q&A at the bottom and type in a question if you like. We'll try and get to them after.
All right, Katie, we ready? 3, 2, 1, lift off. Oh, 1 foot short. But that's okay. The IIT people really hate it when we bash their computers with our cool stuff. So good enough. So thank you so much for joining us for Flying is Complicated. And again, if anybody has any questions, I think we could certainly take a couple before we wrap things up. Katie, do we have any questions from our friends?
All right, let's see. Kaylin, who is 7, wants to know how air is made.
Oh,
maybe where it comes from.
That's a great question, Kaylin. I'm not going to be able to answer that entirely. I can tell you that a lot of the oxygen that's in our atmosphere, because one thing to understand is that our air is made up of several different things. Most of it is gas we call nitrogen. Some of it is a gas we call oxygen, which we depend on for living. There's a fair bit of water mixed into the air, although that amount varies. There's also carbon dioxide, which is something we don't want a lot of and is becoming a bit of a problem. And there's even some rare stuff like xenon and argon. But nitrogen, oxygen, water, and carbon dioxide are the big 4. Now, the oxygen, I can tell you, comes from the effects of living things. Our planet hasn't always had as much oxygen as it does now. And actually, at one point in the past, I believe it had more. It's one of those things that's gone up and down. But most of the oxygen in the atmosphere is pumped out by living things, by photosynthetic plants. The carbon dioxide is sometimes coming from natural processes, but sometimes from human activity, which is one of the things we're concerned about because too much of it affects how heat escapes our planet. The nitrogen, I honestly don't know. Katie, is that something you have any background in about how the nitrogen got into our atmosphere?
No, I do not have background there.
So frankly, I think the best science programs are ones that end with, I don't know, because then you get to have the fun of trying to explore it yourself. So sorry, I can't answer that one, but that might be a fun thing to read about the atmosphere. Do we have any other questions?
I think to end on a question that I think you'll have an answer to, Faith, who is 9, wants to know, what was your favorite flight experiment?
Faith, I'm assuming you mean of the ones I did here. I really like the blower with the big ball, but also trying to do it with the small one. The blower with the big ball is just really fun, and it actually does take a fair bit of practice to get that thing up and to get it moving where you want. But the smaller one, because it takes more precision of you're using your muscles and your lungs and sort of your sense of balance and your sense of perspective. I find that to be more physically challenging. So I like that as well. So those are my two favorite of the ones I did.
All right. Thank you so much, Matt. And thank you for all of the demonstrations. But with that, I do think we have to wrap up. So I'll invite you to say or wave goodbye.
All right. Thanks so much for coming, friends. Take care.
And thank you so much to all of our scientists who joined us today and made those amazing predictions and asked such wonderful questions. If you'd like to see more of our programs, you can head to mos.org/MOS at home to see our full schedule. And if you enjoyed today's program, please always keep in mind that you can support more programs like this by visiting engage.mos.org/welcome. Thanks so much, scientists. We'll see you next time.